So. Okay. So we continue till quarter past?
Yeah. Before the past.
Yeah, good. All right, there were a number of questions there already during the break, and now there's another one. Yes.
Just one question. Could you just clarify what is the averaging in this formula? So
Yeah.
It's about averaging over realizations of a non-equilibrium process.
Yeah, it's an averaging. Yes, exactly. About you do this many times,
Yeah.
and that's.
But like in more precise terms, in terms of averaging over different states, something of that sort. Mathematically speaking.
Okay, mathematically speaking, I can't. Maybe I can't answer precisely, but it is. What it really refers to is that whatever. I mean, of course, it follows different trajectories each time the system state. For example, a two-level system, it jumps at different times between the two states, and this corresponds to different amount of energy exchange with the bath. But when you do this, always starting from this thermal equilibrium with the same protocol, identical protocol, infinitely many times, then you should get this answer. Okay. Yep.
As far as I remember, the total time of the measurement of new realization should be much larger than the initial time scale of the system.
It does not need to be. I mean, are you referring to the time from here to here? No. For the averaging, how many times to average? Okay, so this is another question. Yeah.
Yeah, because the problem is that we cannot do the same experiment many times.
Yes, I think so. Yeah, this is probably the. Okay, yeah, but you have to wait in between always. You have to wait in between. That is important because you need to. For example, let's take a two-level system. You drive it. It may be ending up in the excited state. You have to wait until it really has time to relax back to the equilibrium population again. So, yep, yeah. So the waiting time is important. Yeah. And then another time, the question is how many times to repeat to get this answer. This I don't have immediate answer for that. Experimentally, we do it many times, as you see. Okay, so.
So sorry. So you have the final state has to also be an equilibrium state.
No. No. The final state does not need to be equilibrium state at all. We only know. We just tell that if it is in equilibrium, it corresponds to this free energy here. Okay. So you can drive infinitely fast, and this relation should be valid. Okay, so this is maybe, since we spent quite a lot of time already, maybe I should go relatively quickly through this, because this is you can just you can go through it. You will have the notes. I will send them to you. So this is just a formal original proof of Crooks for this Crooks relation, which in fact then leads to the Jarzynski equality. So we can let's assume that we have a system where when the control parameter, it can be many control parameters, but let's say we simplify the picture here. So you have a control parameter that you change, and then you have the system states. And the work that you do is the sum of this can be written in this form. So E is the internal energy of the system. So it's the sum of changes of this internal energy when the control parameter is changing between the two steps here, without change in the internal state of the system. Whereas the heat can be associated to the change in the system state in an identical manner. So you sum over all the steps, all all the steps in this process. And what holds is the first law. So the change in the internal energy, which is the change at the final corresponding to the final system state and final control parameter, minus the initial system state and the control parameter. This corresponds to work minus the heat. So what do you need to assume here? So this is already now the formal things that we just on a very superficial level went through earlier. So equilibrium in the beginning, meaning that you have kind of Gibbs distribution with this in this form, so that you have this partition function Z and then the populations of this system in the initial state here, which you can write, of course, in this form as well. Then what you need to assume, at least in 20 years ago, when this first time was derived, I don't know how much you can go beyond this Markovianity, but if you keep things simple, if you make the assumption of Markovianity, things are very simple to derive. So you assume that all these individual steps are independent of each other. So you write this probability of following a certain path like this is the probability of these individual steps. So each step individually has a certain probability of going from one state to the other. And finally, you make the assumption of detailed balance of the transition rates of this microscopic states. So the probability of jumping from state ik to ik plus 1 is as opposed to the transition from ik plus 1 to ik is given by the energy difference of the two states times the exponent e to minus beta of this energy difference. Detailed balance is kind of the basis for many things in this business. Mm-hmm.
Should we be in equilibrium in moment, for example, no, this state E0, E2, E1 is it equilibrium? As this equilibrium state?
I0, this one.
Yes.
No. It is just system states. It can jump. For example, two-level system can jump to the excited states due to the coupling to the bath.
And, so it isn't clear what we can characterize this state by only by some macro parameters, and so it isn't clear why Markovianity is quite natural in these Charles conditions. I mean.
It's not necessarily true that it's Markovian, but this is a requirement, at least on this level, to prove this, that you have a system which obeys Markovianity. Yeah.
My question on these states I or equilibrium state, then can the control parameter always be defined? I mean,
Yeah, control parameter.
Parameters like temperature or say a number of electrons in the quantum dot cannot be defined in
No.
equilibrium state.
No. These are for example, the numbers of electrons on the quantum dot, whereas this is voltage.
Oh, okay.
So this is kind of stochastic thing what's happening here, and this stochasticity depends on the coupling to the bath. Yes, exactly. It is a knob. This is a thing that you can control precisely in this, and this is the stochastic part of it. Okay, then you can write this chain, and I will not go into details now here, but it's simple. So you take the probability of going from this initial state to the final state. at parameter lambda n, in, and divided by going backward, in lambda n, going from this to the I0 lambda 1 or lambda 0. And you can, because of the Markovianity, you can just make it into the product form here. This you know that they come from the equilibrium state, because this is the initial state in each case for forward and backward process, and these ratios are given by the detail balance. And finally, what you find from here is that exactly this ratio of the probabilities e to beta w work minus the free energy difference with this notation. So one gets exactly this Crookes relation that these probabilities for forward and backward probabilities obey this e to beta dissipated work. And from this, one obtains the Jarzynski relation very, very easily, because you can write down that the expectation value of this exponential here, e to minus beta wd, you can write down it as the integral of all the possible outcomes of your measurement of wd, weighted by the probability that this can occur, integrated, and then using the Crookes relation, you get it into this form. And then you can make, for example, simply a change of the integration variable from minus wd to wd, and due to the norm of the probability that it's 1, you get that its Jarzynski equality holds. Yes.
Sorry, one of the assumptions you did on the previous slide.
Sure.
The equilibrium, the population, population ratios, detail balance for the
Detail balance, yes.
So is it some kind of adiabatic approximation? Because I have to admit it says that at every step of your control parameter movements,
Yes.
you have some kind of equilibrium calculation.
No, the populations are not equilibrium. It is just that this transition between these microstates is governed by the temperature. For example, you can have whatever. you just change your control parameter, and then the transition rate, say, from low state to the up state versus the transition rate from up state to the down state is given by this detail balance. This is usually the case with equilibrium bias, for example, for a tunneling process.
I think the confusion is because, so if we have a non-equilibrium state, so for example, when the system is in between lambda 1 and lambda 2,
Yeah.
The system has a probability to decay to other states. So in the full formula, there's a probability, there's a factor of the system staying in that state.
Uh-huh.
When we take the ratio of these, they cancel out.
Yes.
So we are left with only these microstate probabilities.
Yes. Yeah, I don't exactly know which confusion, but that's where it comes from. Okay.
Comments about the table balance in equilibrium. In equilibrium case, that it isn't clear why we can't characterize this one. I mean, your states can be characterized by macro parameters.
Yes.
And it isn't clear why it depends only on these macro parameters like an energy with table balance.
Mm-hmm.
Could you explain this? No, I mean, this one. Why should we expect what this ratio should depend only on such macro parameters like an energy?
This one.
Yes.
Okay, so I think in any state, if, for example, you can also take like a qubit, you can put it to some state, and the probability that it makes the transition up to the excited state is given by exactly this, the temperature of the bath and the energy separation. So whatever state you are in, the system makes a transition which is determined by the bath. if the system is coupled to the bath. The transition rates can be large or small, but the ratio is given by this.
So even if you have the strong coupling with the bath, you also can say that detail balance is a single.
Strong coupling is a dangerous word, of course, because if you go to the very strong coupling, then you can't even separate the system and the bath anymore.
So all
It's kind of a weak coupling. We at least in weak coupling we are safe usually. But maybe we see examples where this is true later. It's an assumption. I mean, look, this is if you assume that this is true, then everything follows. Whether it is true, it's not all. Definitely, it doesn't have to be always true. But I would say that at least in the systems that we are looking at, this is usually the case. Okay, so let's then go to some realizations, simple realizations. Maybe some things become more clear in that case. So what we are looking at is a very simple system, like a single electron box. Okay, so did anybody explain the single electron box here before? No, I think not. Yuli was explaining it, yeah.
But Beethoven, for example, showed
So the single electron tunneling is a topic that was very popular maybe 20, 30 years ago. And then as such, of course it's still important, for example, for some applications like creating single electron sources, current standards, for example, or of course you can say that charge type qubits are also related to single electronics. So it's important basis anyway. So let's take an example of a single electron box here first. So in a single electron box you have one tunnel barrier. It can be metallic, it can be semiconducting, and then there's an island, like we had this quantum dot there, and in this island there's always an integer number of electrons, and you can control this system by a gate voltage, or say voltage. It's like in the first case that you can really tune the energy landscape by a voltage there. And it's coupled through the gate capacitance here. So there's an electric field that acts here, and it polarizes electrons to this capacitor here. And then this tunnel junction also, because usually it's like in a metallic case you saw that there was an overlapping area. So this also has some capacitance. It's kind of a leaky capacitance. You have a oxide barrier, and then you have the metallic contacts, and it's like a parallel plate capacitor between the two. And we can determine the value of this capacitance, and let's call it C. So the energy of this system, the relevant energy, free energy you can call it, can be written in a very simple form. It's like this. And maybe we can even, do you mind if we go through how you obtain this? Is it okay? Yes? So anyways, what you get is that there's an energy which is a scaling EC, which is determined by the capacitances here, times the N minus Ng. N is the number of electrons here, and Ng is the normalized voltage acting on this. So it's kind of the polarization of this island. So what this leads to is that you have energies of this system which are parabolic in, I mean here now, important. So this is the stochastic variable, this N. It can change if the electron tunnels in or out. This is the control parameter lambda, which you just control precisely. So this is lambda, this is I. Okay? So if you change the control parameter Ng, which is here, you will have, for different values of electrons on the island, you have these parabolas centered at the integer values of n. And for example, if you stay around 0 voltage, then it's preferable to have no electrons on the dot, because the energy is minimal. If you go away both ways, if you go far enough, you go through the degeneracy, and then another charge state becomes preferable, so the electron prefers to tunnel and stay on the island or go out. Okay? But then we have finite temperature, so even if you sit here, sometimes you can be sitting, you can go to the wrong state or to the excited state and back. So this is the basis by which we can do this stochastic thermodynamics with a single electron box simply. And okay, let's look at this, how this energy of this system comes, because there are some important concepts there also, which maybe are forgotten there, and which were discussed already here earlier. So we can write, for example, we can write the capacitive energy of this box as such. We'll look at it, all the capacitors, how much energy is stored in these capacitors. But in order to find the relevant free energy of the system, you have to take into account also the work that you do by the source that you couple to this system. So the total okay, we can say that the relevant energy is the one minus the work that you do by the source. So it's the internal energy minus the work done by the source here. And of course, if you have many sources, you need to take into account the work done by all the sources coupled to this system. If you have a voltage bias like we have in most cases, then the work that you do is essentially work is, as we saw before, you have like a power which is I times V, and then the work that you do is equal to integral of this over the time. Okay. So if you have a voltage bias, then you have simply voltage times integral of I dt prime to t. So it's equal to the and the integral of the current is charged, so you have V times Q that you load to the system. So this is exactly what we want to now subtract from the internal energy of the box in order to get the relevant free energy, which matters for this kind of thermodynamic consideration. And so let's just write it down for the simple box. So I put it back here. So I draw it here again. Okay, let's draw it here once more with the proper notation. So we have here this Ne, and let's call that it has a potential U, this island. Then we have this tunnel junction with C, and then we have gate capacitance Cg, and then we have voltage Vg, and we can of course choose the zero of the potential as we like. So, and this is elementary to obtain the charging energy. So we write down first that the internal energy in this case, or say the energy stored in this capacitors, is equal to 1/2 times C times U squared. That's the capacitive energy here, plus 1/2 times Cg times U minus Vg squared. Another equation that holds here is that the charge here on the island, the total charge on the island, which is integer, let's say that we can choose sign arbitrarily, but we get maybe a neater form when we choose it so that E has a positive sign, and then we have n electrons on the island. So this is equal to C times U plus Cg times U minus Vg. So now you can solve for the potential of the island, which is simply okay. So U is Cg Vg minus Ne over C sigma, where C sigma is the sum of this is C plus Cg. Okay. The total capacity. Of course, there could be some extra stray capacitances, whatever, and they would add up to this one as well. So now I will not write it precisely here. I just I ask you to do these steps. So the internal energy comes now when you just plug in this value of the potential of this island to this expression, you find that it becomes like Ne squared divided by 2 times C sigma plus constant, which we ignore. Constant in there's just terms like Cg, which depends on Cg and Vg, which we have control parameters. And then we will take the actual energy, which is E internal minus this Qg times Vg, where now our Qg is where Qg is Cg times what was our sign convention? So Vg minus U. And when you plug this in, I ask you to go through these steps. You find out that this energy is equal to E squared over 2C sigma times N minus Ng squared plus constant. With this notation that we have here. Okay. Okay, I write it here so that it's directly visible, so nothing. Vg over E squared. So what we have is like we have a charging Hamiltonian, which is extremely simple. So it's just it's the simplest realization of having a control parameter and having a stochastic variable to do stochastic thermodynamics experiments. Okay. So before showing any experimental things, so let's see when is this kind of, so in order to do some kind of well-controlled experiments, we would like to have the system in the two, to be in to have only 2 possible states for it at each control parameter. And in order to do that, you need to require that this charging energy here is clearly larger than temperature. And this one finds out that for typical systems, I will not go to detail here. So you have an island which is coupled to, for example, through tunnel junctions, and you need to ask that this charging energy is clearly larger than the temperature, and in this case, if you just plug in the parameters of these typical tunnel junctions, you find out that that these charging energies are typically 1 Kelvin, so you need to work in the millikelvin temperature range. And this is the basic experiment. So let's look at it here. So what we have is we have here a single electron box, which is a little bit different from what I showed here. It's kind of this is an interesting single electron box in the sense that we have one tunnel junction and it's coupled to 2 islands here. So the electron can indeed, an extra electron can be either on the left side or on the right side. So if you look at it, the number of charges on this system is always a constant. But the extra electron can be on the left or on the right side. So now when you apply a gate voltage to this through these capacitors here, you can drive the system to go either to the left or right. The realization of this system is shown here. So this is the left island, this is the right island, the tunnel junction is here, overlap junction. And by applying a voltage to these electrodes here between these two, you can change the gate. And then you can detect the number of electrons, for example, on this island, by putting a single electron transistor here, which is like this quantum point contact. It's something where the current through this single electron transistor depends on the population on this island. So if there is an electron here, it's again there's some Coulomb repulsion in this system. So now now how much heat do you generate in a transition? So suppose you are sitting at some position here of gate voltage, for example, away from this degeneracy between them, and we operate in the gate range, which is in this range, so to say. So then the energy that you dissipate in a transition is given by the difference of these parabolas. So it is you can see that it is simply, if you take the difference between E n equals to 1 minus E n equals to 0, and plus minus depending on the direction of this transition, you get that it is 2 plus minus 2 EC times Ng minus 1/2. Okay. So this much is released energy in a transition when you make it. And now if you are changing this control parameter in time here, and you know the value of the control parameter at each time when the transition occurs, you can determine how much heat you produce. So for example, here you know that you have a certain value of the control voltage, and then this transition occurs, which you detect by the detector here. Then you can assign this much heat to it. So you don't directly measure the heat, you just measure the transition, and you tag on at what position it occurs. So then the total heat in this process, when you, for example, drive the system from this point to this point deterministically, and there are transitions occurring along the way, is the sum of all these heats in these different transitions. Okay? And if the system is also, if the internal charging energy changes in this, or this charging energy changes between the endpoints, then you may have some internal energy change as well. So, and here is the realization of the experiment. So what one does is that one changes the gate voltage in time, like this, and it corresponds to moving between these two minima here. So you kind of sinusoidally move the gate between these two values, and you record the transitions in between. So basically we assume that it's always in equilibrium when you reach here at the extreme of this excursion. In fact, it always makes the transition finally, so that's why it's a good assumption in this case. So you can see that the detector, which is measuring the number of charges here, is kind of making more or less a synchronized sawtooth here, or square wave response here. So always when you come close to this degeneracy, there's a transition from one state to the other. However, you can see that sometimes there are many transitions, and all of these contribute to the heat that is produced. So if you zoom up, for example, one of these half periods here, you can see that there are many transitions up and down. And now if you evaluate the heat on those transitions, because you know also the gate value here at each transition, you can reconstruct the work that you do in this kind of a drive. Okay? So if you do this now many, many times, so ideally infinitely many times, you can construct a histogram of how much work do you dissipate here. Exactly to do this for the test of the Jarzynski equality. So what you do is you measure, you change, for example, you use a fixed frequency of this drive. So you kind of in fact, each half period here is a repetition of same protocol. So what you have is that if you do this very slowly, then you get a distribution which here looks quite Gaussian, because it's parabolic here because it's on a logarithmic scale. So this is a probability of obtaining a certain value of dissipated work in a certain in one realization. So it looks Gaussian. It's a little bit shifted to the positive side because, of course, the second law says that you have to, on the average, dissipate energy in this case. Sorry? This is probability. Yeah, probability. No, it's probability density. So you have to integrate. Mm. So, and if you would, in fact, if you would go infinitely slowly, theoretically what we find is that it becomes a delta function, of course. So it's always, you have zero dissipation with, and all the realizations have the same answer. But of course in experiments we can't do this. We have a lot of experimental problems. If you go too slowly, there are some changes of the setting background charge changes in the system. So we can't, this is maybe the best we can do. So we get a Gaussian, essentially Gaussian distribution. In fact, the theory predicts that, which at that time we were doing it, so predicts that at slow speeds it is Gaussian, but it is shifted. It's a precise expression for that. If you increase the rate of the frequency of this, you can see the red one is double frequency and blue one is 4 times larger frequency. You can see that the distribution is becoming more kind of skewed. It goes more to the positive values. Of course, you dissipate more energy, but nevertheless, this. So then you can, what you can do is you can really, you can just find by integrating this exponent of this thing, you can find that the Jarzynski equality is valid within about 3% or so in all the cases. And what is important here is, of course, that you have a lot of events when this work is, dissipation is negative, even in this case. So this gives us a possibility to, if we can detect these realizations where the work is negative, you can maybe make use of this thing. And this is the basis of the Maxwell's demon then. The Crooks relation is also valid. It's a little bit difficult to prove it on the very wide energy range though. So I think we are almost done as to the time. It's till
It's until half.
till half past. Okay, okay. I- Maybe I'll continue a few minutes. Yeah, just. It should be all now, right?
Yeah, yeah.
Okay.
It was just too interesting.
Okay, so let me give you something which is okay. So Maxwell demon. So who knows the basic Maxwell demon? Not everybody. Okay, so let me explain it. It's a thought experiment, of course, initially, and the important thing is that now it's not anymore a thought experiment. So suppose that that this was like 150, 160 years ago. So suppose you have a chamber with two halves, and it's filled with molecules or particles, whatever, and then there is a then there's a wall in between. There's a door in between which can be opened and closed. So then, let's say initially the door would be open and everything is in equilibrium. You have the same temperature on the left side and on the right side. But then there is some intelligent being here who is looking at these particles on the level of individual particles. So always when, say, a fast-moving particle is willing to move from right to left, he opens the door, and on the contrary, if the slowly moving particle moves from left to right, he or she opens the door. So eventually, what happens is that the distribution is such that on the right side on the left side you have a lot of fast-moving particles, and on the right side a lot of slow-moving particles. So you create a temperature difference, so you create a non-equilibrium. And ideally, this can be done without doing any physical work. I mean, everything can be lubricated very well. And so, in principle, this can you can really violate the second law by doing this thing here. So, and there have been some experiments now on this in the last few years, and one of the first ones was this one with a kind of some microspheres or some small particles, where the idea of the experiment was the following. I will not go into the detail how it was realized. So the idea was that, of course, if you have kind of a ladder, the particles move down, and then if you have somebody who is watching these particles, sometimes due to the thermal excitation, the particle can jump up, and then one can just put a wall in here to prevent it going up, and eventually you end up having particles collected up at a high potential, so you kind of have a source of work, some increase of the energy of the system. All this is somehow related to information. So information is put on the same footing as the entropy. So we'll come back to this in the next lecture. But anyways, what one finds out that there's mutual information. This was a paper by Sagawa and Ueda about 9 years ago, where if instead of using the standard Jarzynski equality, you also include the mutual information. So that's related to the measurement probability. So if you measure the system state precisely, then you can then this mutual information is a significant thing here. And this way you can really win the second law of thermodynamics. So you can do work which is smaller than delta F if your mutual information is something finite. So it relates to this, that how well this guy is here really monitoring the particles going in and out. But the simplest, so I finish with this, the simplest Maxwell's demon which we realized in the experiment is the first one, is so-called Szilard's enzyme, which also an idea almost 100 years ago by Leo Szilard. So this is like a single particle demon. So suppose first you have a single particle in a vessel, and this particle is thermalized with the walls, so it's moving there at having the energy determined by the surroundings. And then there is this being, this demon, who at some moment puts a wall in the middle of this compartment here, or this vessel here, and then detects whether the particle is on the right or on the left side. And if it's on the right side, then connects a weight to the right side, and after that the particle which is still interacting with the surroundings here pushes the wall back to the original position. So we'll look at this in the concrete example of our electronic system, but now if you do a naive estimate of this isothermal expansion of the single molecule gas from this position to that totally moved position, this gas does work against the load, which you can write down as the expansion P dV. And if you use naively, if you use just the ideal gas equation of state, you have this integral which gives you kT logarithm of 2 by expanding from half volume to the full volume. Although this is of course very kind of shaky argument on this level, but you will see that due to entropy arguments also, for example in our electronic system, this is the result that you get, that by making use of this information of a particle being either on the left or right with these equal probabilities, half division, the work that you can extract or the heat that you can extract from the bath is equal to kT log 2, which is the quantity that you will see many times in this business. So I think I finish here. So we'll next look at the experiment on this Szilard enzyme tomorrow, and then we move to real measurement of temperature and heat in the bulk of the next lecture. Yeah. All right.
Okay, if anybody has some questions, you are welcome.
But it would be a crime against the cook, so be careful.
Okay.
Yeah, not too long.
Not too long.
If you have one.
Could you go one slide back, please? Does the information term as a rate factor of 1 over kT or not?
Okay, so no. This is just you subtract from in the exponent this information, because this is like the entropy term here, work divided by kT.
And in the line below, is there...
Here. So the units. Okay. So let me see. You are right. You're right. Yeah. IKT. Yeah, sure. You're right. Yeah. No. That's what I said, that this is just the toy argument here. We'll see it for the real system, how it goes. But this is the answer that you always end up.
Be careful, the cook had threatened to make Russian stew before.
No questions, right?
No, maybe at the table. Thank you. Okay.